Hello everyone, my name is Najdet Charaf and I want to give my presentation on RVCAP, enabling dynamic partial reconfiguration for FPGA-based RISC-V system on chip. I would also like to thank my co-authors and especially thanks to my Professor Diana Gohringer. So here is the outline for this talk. I am first going to start with the motivation, then I want to talk about the reconfiguration management in detail, starting from which SOC we used to taking a look or a detailed look into the RVCAP controller. Then I want to show our results and evaluation, starting with what we additional support with this solution and resource evaluation, reconfiguration time, the comparison with the state of the art, and which application we used. And at the end, I want to end my presentation with a summary and concluding remarks. So in the first two slides, I want to highlight 2 points. The first one is the system on chip. Systems on chip are gaining more and more importance, and their field of application is continuously expanding, and they are increasingly implemented on programmable chips. These chips called FPGAs. On the right side we can see an overview of a SoC on an FPGA, which consisting of a processor, some hardware accelerator, and some controllers. Basically a SoC using a master processor, which can be either a hardcore or a soft core. A hardcore processor is available as a macro, like the ARM Cortex A53 processor, which we can find on Xilinx Zynq FPGA. The soft core can be synthesized from source code, either a vendor specific like microplays or an open source like a RISC-V instruction set. Here I just want to mention the vendor specific. You cannot see into the source, so you have to take it like an IP core. So if you want to give this SoC the ability to be adaptive, so we need to provide and implement a suitable reconfigurable management, for sure together with the necessary hardware components and the software drivers. The second point is dynamic partial configuration. I will say that you have already heard about this feature, and because this feature has been increasingly available to the engineering community in the last year. So this function is time multiplex, and you can modify the hardware functionality at runtime. So loading a hardware accelerator like a library, a software library, has now become a possibility. At the right side, we can see here a design with 3 reconfigurable regions and 4 reconfigurable modules. So if you want to change the behavior or the functionality of this reconfigurable region from blue to red, you only need to load the partial bitstream from red into this region, and you're doing this without interrupting the functionality of the rest of the design. And commonly, the reconfiguration process is controlled by a processor, like I mentioned, either soft core or hardcore. So let's talk about the motivation of this work. In the last years, a lot of works and approach has been proposed for managing DPR, and also other project has been proposed for supporting RISC-V. But none of the previous work combining an open source RISC-V processor with DPR, so this is still missing, and adoption of a new instruction requires the development of new softwares, sure, along with the hardware components. So the goal is to bring the two domains, the RISC-V and the DPR, together. The solution will be using the RVCAP, so it means this work. So to the best of our knowledge, our proposed work is the first solution for managing DPR for FPGA-based RISC-V system on chip. So let's talk about the reconfiguration management. The SoC we used is an open source RISC-V Ariana 64-bit. and we use it as an XE4 based system on chip. Here we can see the Ariana core we can see the Ariana core, which is the master unit in the SoC, and all the other periphery will be are slave memory mapped. We also add other component like an AXI clock converter, which convert the 200 MHz to 100 MHz, and the AXI isolate, which decouple the RP regions from the static during the reconfiguration process. And we also using the on-chip memory to load or to store the application instructions. We use also the RISC-V GNU compiler toolchain to generate executable application for the Ariana core, and we developed other IPEs to access and combine with the whole memory mapped peripheries. So here is now our RV cap in detail. The controller consists of 5 main components. The DMA controller, which is for transferring to and from the DDR, the access stream switch, which is for selecting between two modes, the reconfiguration mode, which allows us to reconfigure the target RP and loading the partial bit stream from the DDR to this target RP, or the second mode is the acceleration mode, and here we can transfer the data from the DDR to the target RM. Then we have other components like access stream to ICAP, converters, and other controlling interfaces. So we also see that the controller has 4 interfaces, 2 at the top to the main AXI4 crossbar, and 2 interfaces at the left for transferring the data, as I mentioned, to and from the DDR. Also, we can see here that the interrupt control signals from the DMA are directly connected to the process level interrupt controller plaque, and this is supporting the non-blocking mode during data transfer and free up the processor for other tasks. All the components are working at 100 MHz, and the controller provides a high data throughput rate. This we can see then later in the evaluation section. The reconfiguration process is divided mainly in 3 steps. The first one is initialize the RM. So we count here how many RMs we have, reading the partial bit stream size, moving the partial bit stream from the SD card to the DDR. Then we decouple the RP, like I mentioned before, from the static part, and then the main part is to reconfigure the RP. This starts by enabling the DMA reading and writing channel, followed by selecting the DMA configuration mode, and the writing and transferring the partial bitstream data. All these steps are managed by Ariana, and like I mentioned, the non-blocking mode is here selected. And at the end, an interrupt signal is sent to the PLIC to indicate a successful completion of the reconfiguration process. What about the software drivers? We use the update mem utility from Xilinx to update the boot ROM data inside the bitstream and to provide more flexibility during the system design. What about the purposes? There is control, execution, and evaluation purposes. Like I mentioned before, also the access to this peripheral and providing the user input and output functions. We have an utility IP. This uses functions and macros for memory map periphery access. We have a file IP for reading and writing from and to the SD card. This is accessed via the SPI. And then we have also the timer and the user IO IP, measured the time required for function call in microseconds, and for user input and output during runtime. This will be over the UART. So here this figure will show us the sub-steps for using the update mem utility. So using this utility avoids any resynthesize or re-implementing of the hardware design, and we need here three files: the full bit stream, and the memory here, the memory file, which is the .mm, and the memory map information, the MMI. So, and all these steps is, we automated all these steps with a MAC file. So let's go to the results. So what I said that about supporting vendors, so we allow that the IP from the Xilinx to be controlled by the Ariana. To achieving this, we adding two converters. The first is the data width converter from the 64 to 32, and the protocol converter from Axi4 to Axi4 Lite. This is to meet the specification of the IP. And then we also resize the internal write FIFO to 1024 to improve the time transfer. The reconfiguration process here is similar to the RVCap, but the difference is in the reconfiguration function. Here we can see the difference between the RVCap and the HWI cap, because here we have no DMA controller. We are using the internal buffers of the IP. On this slide, I want to talk about the resource evaluation and reconfiguration time of the RVCap. So we use the Xilinx Vivado design suite 2019.1. We use the board Genesis 2, which is a Kintex 7 FPGA. All components are, as I mentioned before, are running at 100 MHz. The IPEs are implemented in C, and the reconfiguration time is measured by the CleanIt component. In this table, we can see the resource utilization of both RVCap controller and the HWI cap, or using the HWI cap in our SoC. Both are divided in two modules, and here are the resources for each controller. We can see here that the HWI cap occupies fewer resources than the RV cap, but in return we can see here in this value that we get only about 2% of the theoretical maximum ICAP throughput. The figure on the right side show us the difference between the graphical difference between the RV cap controller with the DMA and the HWI cap IP from Xilinx. And we can also see here the difference in terms of different RP size, and which is also generate different partial bit stream size. And we can see here from partial bit stream size from almost a half megabyte till 2 megabytes. So, and if we can see here, over all regions and partial bit streams, we achieve at maximum throughput of 398.1 megabyte per second using the RVCap controller inside the all component what I already mentioned in previous slides. In this slide, we see the conversion with the state of the art. So from the table, we can see there were several DPR controllers and several pushes for managing DPR, but they are not adapted for integration with RISC-V processors. So you can see here there is a microplace, there is an ARM, there is again an ARM and Leon 3, but no RISC-V. In this column, we see that we compared in a fairly way all with 100 megahertz. So comparing to the first line, we can see that, or we assume that the IPs we developed lead to an execution overhead that reduces the maximum achievable theoretical throughput by 1.9 megabyte per second. But nevertheless, we achieve with the 398.1 a very high throughput rate for the configuration process. About the application we used three different image processing filters, Zobel, median, and Gaussian. These filters are developed using Xilinx Vivado High-Level Synthesis (HLS) tool with 64-bit axis stream interfaces. The image size 512 by 512 pixels, a 8-bit to represent 256 gray values. The RMs we use here, or the functionality here also are running at 100 megahertz. The images are stored then in the DDR memory to be loaded by the RV-Cap controller, as I mentioned before, in the second mode, in accelerator mode or acceleration mode. The figure here shows us an overview of the full system-on-chip flow plan on the Kintex 7 FPGA. Here is the table for the resource utilization of the whole system on chip. Here we can see the RP size and each image filter, and here is the percentage utilization of the RP. And here we can see that the controller, the RV-Cap controller, consumes only 3.25% of the total system-on-chip resources in terms of lookup tables and flip-flops. Now let's go to the summary. We could propose a novel reconfiguration management to enable DPR on FPGA-based RISC-V systems. We also support a set of development software which running on the Ariana processor. The DVR controller achieved really high speed reconfiguration throughput of 398.1 megabyte per second. We provide also a controlled stream interface between the DDR and the corresponding RM. We also support vendor controller like the HWI-Cap IP. About the future work, we plan to porting the design to other FPGA devices that support DPR and adapt the work to other RISC-V SoCs with an XC4 bus. So this brings me to the end of my talk. Thank you for everyone who attended this presentation, and especially thanks to the paper sharers and the organizers for letting us presenting this paper remotely. I hope everyone has great time at IPDBS.